Okay, next we move on to the mechanism of protein denaturation. In the native state, the protein is comprises of a hydrophilic surface, okay, and a hydrophobic core, okay. And during denaturation means it undergoes either non-physiological condition, for example, addition of acid, addition of alkaline, denaturing agent, or under physiological condition like mechanical action, whipping, okay, cooking. The hydrophobic core will resurface or will be introduced to the surface. Okay, this is where the unfolding begins. Okay, so it forces the hydrophobic core to the surface, and when it goes to the surface, it aggregated with the another native molecule of protein, and that is why denatured protein change in terms of physical appearance. So initially liquid egg, after boiling, becomes solid hard boiled egg. So what are the consequences of denaturation? First is improve in terms of digestibility. So denatured proteins are more digestible compared to the native protein. Secondly, when protein undergo denaturation, of course, it will lead to loss of solubility, okay, due to the surfacing of the hydrophobic core. So denatured protein will have a greater tendency to aggregate. Thirdly is change in texture. So protein denatured, of course, will change in terms of the texture. The fourth one is denaturation of protein will improve forming and emulsifying property. So back to the earlier slides, when protein undergo mechanical action, whipping or whisking, it will form foam. So denaturation of protein have better forming characteristic. Emulsifying also will be better, okay, because denatured protein will have both hydrophobic and hydrophilic characteristic. So that is why soy protein is used to increase forming and emulsing for property when they becomes denatured. Okay, so if you look at chocolate packaging, you will have you will see one of the ingredient is soy protein lecithin. So lecithin is the emulsifier, okay, used to mix non-polar component and polar component of the chocolate. Last consequences of protein denaturation is affecting the sensory of the product. Okay, for example, in beverages containing protein, the solubility of the beverages, of course, has to be high. Okay, the solubility of the protein in the beverages has to be high. So therefore, if during processing leads to denaturation of the protein, it will lead to precipitation and flocculation during the storage, and therefore it will affect the sensory of the product. It is no longer in a soluble form. Okay, it becomes mixture of solid and liquid which is undesirable. So look at this question here. Tannic acid is used to form a scab on a burn. An egg becomes hard boiled when placed in hot water. So what are the similarity between these two processes here? Okay, both leads to protein denaturation. Okay, the first one is acid as the denaturant, and the second one is heat as the denaturing agent. So next we look at what are the major interaction which influence the solubility characteristic of a protein. So the first one is hydrophobic interaction. So when protein and protein, one native state of a protein interact with another state of a protein, okay, this will result in decrease in solubility when it becomes denatured, okay, because the inner core of the hydrophobic surfaces, so it tends to agglomerate. So when it agglomerate, therefore solubility decrease. Secondly is ionic interaction. Ionic interaction normally occur between protein and water, and when water is very powerful polar solvent, so it will result in increased solubility between the protein. Okay. So if the major interaction are hydrophobic, means the protein solubility decrease. Major interaction is caused by ionic, means high solubility. Now protein solubility also dictated by the hydrophilicity and hydrophobicity of the protein surface that is in contact with the surrounding water. Go back to the native structure of protein, in which the inner core is hydrophobic and the surface is hydrophilic. So if major hydrophilic is on the surface, means it is soluble. If most of the side chain of the amino acids are the nonpolar or the hydrophobic, it is lower in terms of solubility. So few number of surface hydrophobic, so better solubility. Okay, next we look at protein solubility. So based on solubility, protein are classified into four category. Four category means soluble in water, soluble in neutral condition, soluble in acid or alkaline solution, soluble in ethanol. First we look at albumin. If you notice, all of the listed protein here are the simple type of protein. Okay, albumin normally found in protein whey milk, is soluble in water at pH 6.6. Globulin, for example, can be found as glycine in soybean and also in milk, soluble at neutral condition. Glutenin and prolamine are highly hydrophobic proteins, and glutenin can be found in rice and also wheat, and soluble only in very acidic and very alkaline condition. prolamine, soluble in 70% ethanol and can be found in corn and also wheat. Scleroprotein, insoluble in water and also neutral solvent. An example of scleroprotein are the fibrous protein, collagen of muscle tissue, gelatin, elastin, which is a component of tendon, keratin, which is component of hair and hoof. Next is histone. Histone is soluble in water. And then last is protamine, which is strongly basic protein and can be found from herring and scombrin from mackerel fish. So next we look at factors which affect protein solubility. The first factor is polar solvent. So protein are soluble in strongly polar solvent like water, glycerol, formamide, dimethyl formic acid. Second factor is pH. Now protein are soluble at pH except isoelectric pH, because at isoelectric pH the solubility is minimum. Okay, and this is called isoelectric point. This is where Zwitter ion is formed, which leads to the minimum solubility of protein. So majority of our food protein are acidic protein, okay, which is the sum of aspartic acid and glutamic acid residue. Okay, and these two acid residues are greater if we compare to the sum of lysine, arginine and histidine residue. So therefore this majority food protein containing aspartic acid and glutamic acid residue will have minimum solubility at pH range of 4 to 5, and this is classified as isoelectric pH. And most protein are very soluble at alkaline condition, alkaline pH, which is in the range of pH 8 to 9. So why minimum solubility of protein at isoelectric pH? Go back to the rule of thumb, the hydrophobic interaction and also ionic. So if minimum solubility means the major interaction that contribute to this is hydrophobic interaction. Okay, so lack of electrostatic repulsion, and it will promote aggregation and precipitation. However, there are exceptions. Okay, some food protein are highly soluble at isoelectric pH. For example, beta-lactoglobulin, in which the isoelectric pH is 5.2. And also bovine serum albumin, which is the isoelectric pH is 5.3. Why is this so? Go back again to the rule of thumb. So if it soluble means the major interaction will be hydrophilic interaction or ionic interaction. Okay, so large ratio of surface hydrophilic residue, okay, on the surface of the protein. The next factor is temperature. So as temperature increase, protein solubility also increase, but there's a cut-off temperature, which is 40 degrees Celsius. So more than 40 degrees Celsius, protein solubility will decrease. And why is this so? Denaturation. Remember, denaturation occur at high temperature and water in the presence of denaturant also. Okay, so therefore protein solubility increase as temperature increase, but only up to 40 degrees Celsius. Okay, next we move on to emulsion. So what is emulsion? So emulsion are fine dispersion of one liquid into another. So basically it involves two immiscible liquid. So generally oil and water, those that does not mix, and one liquid forming the continuous phase, or we call it dispersion medium, and the other will be the dispersed phase or the liquid droplet. And there are four types of emulsion: oil in water, O slash W, water in oil, W slash O, water in oil in water, or oil in water in oil. Both of these are double emulsion. This figure shows the types of emulsion. The first one is oil in orange color, oil in water, white is water. Second one is water, okay, the white circles are water, blue colored are oil. So water in oil. So the third and the fourth figure here represent double emulsion. Okay, here we have water, white colored, water in oil, orange, in water emulsion. And this one, blue, is oil, white, water in oil. Now, example of oil in water emulsion include milk, cream, mayonnaise, soups, sauces, chocolate milk, and infant formula. Example of water in oil is butter and margarine. Emulsification. So protein are a very good emulsifier. Okay, commonly used emulsifier means they are amphipathic. Okay, having both hydrophilic and hydrophobic characteristics. So therefore they are able to mix oil and water. So protein emulsion can be used in big products, in ice creams, in salad dressings, and coffee whiteners. An excellent example emulsifier is, as I mentioned previously, is lecithin from soya bean. Okay, soy protein. So to create lecitinated soya proteins, lecithin is mixed with the protein, which make them dispersible. Okay, and then added to the product. Okay. Foaming is defined as colloidal dispersion, where gas phase is dispersed into the liquid phase. In the case of egg white, when you beat the albumin or component of the egg white, the air will get trapped, and this will cause the formation of a foam. That's why the characteristic of foam is light, okay, due to the air that gets trapped, okay, during the whipping or the whisking. Now foam consists of aqueous, which act as the continuous phase, the egg itself, if that is the material used, and gaseous, which is the air dispersed as the dispersed phase. The texture of foam is similar, like ice cream, like bread, like marshmallow. It has that unique filling in the mouth due to the air bubbles that dispersed in the aqueous or the continuous phase. Protein stabilized form can be formed by shaking a protein solution and then it will form a thin layer at the liquid gas interface, and it should be able to incorporate large quantities of gas bubble. So the forming property of a protein is measured based on its ability to form a thin tenacious film at a gas liquid interface, so that large quantity of air bubbles can be incorporated and also stabilized once the form is formed. So if you notice, when you beat protein, okay, or you beat egg, you will see the form is at the upper layer, and the lower layer is the remaining liquid that initially was undergo the beating or whisking. Now, formability or forming capacity of a protein can be calculated as overrun. Okay, overrun means steady state form volume, or forming power, or form expansion, and the formula is volume of the form, okay, divided with the volume of the initial liquid used. And then to calculate the forming power, the volume of the gas incorporated divide with the volume of liquid times by 100. So what is the mechanism behind the forming of protein? Okay, let us take egg protein as an example. So when egg protein undergo whisking or beating, it becomes denatured. So means unfolding of the protein structure will happen. So this unfolding will leads to the formation of a long axis of polypeptide chain here. Okay, and this will be parallel to the surface, okay, which is in contact with the air. So one of the property of denaturation is decrease in terms of solubility. So protein will decrease, the egg protein will undergo decrease in solubility, and then at the same time coagulation will occur, okay, between the albumin of the egg component, okay, and this coagulation of this albumin at the same time will entrap at the surface here, okay, entrap air, okay, and it will form at the upper layer, and the lower layer remains the continuous or the aqueous phase. So as you beat harder, okay, or the mechanical action is prolonged, okay, the air is entrapped and it will stretch the albumin, okay. So here is the picture showing forming of egg, okay. So this is the egg, okay. First of all, you broke the egg inside the bowl, and then you whisk it, and as you increase the whipping process, okay, the air will get more entrapped in the stretching of the albumin, and then you get a lightweight of foam material here. And that concludes the third part of protein.